What I'd like to do in this video is demonstrate how to calculate a correlation using a formula. And I'll do this both for a strong correlation and also for a weak correlation so that you can see the difference in the calculations. A couple of words about the history of correlation first. The Pearson correlation was actually devised by Francis Galton, and he published the concept in 1890. He discussed it as early as the middle 1870s in various different publications of that time. And Pearson, in contrast, was born in 1857. He was a student of Galton, and for some odd reason, it's called the Pearson correlation, even though the concept itself originated with Galton. And there's a very nice article talking about the genesis or origin of the correlation as it was devised by Galton. You can refer to this article by Stephen Stigler. It's available for free online. You can easily find it if you just Google it and download the PDF. Also, Stigler has an excellent book on the history of statistics if you're into that sort of thing, where he talks about these and other issues. One of the things that Galton did is he devised what's called the Quincunx, which is Latin for 12/5. That was a coin in the ancient Roman period. And it's given that name because of the essentially the 5 sides. So if you have a dot with 5 points around it, so if you consider this dot right here that my pointer is on, and then the dots at the 4 corners, that makes 5 total, like the points within the number 5 of a 6-sided die. Galton devised the Quincunx board, or Galton board, really as a demonstration device where he can show that the properties of the central limit theorem apply to shotgun shot if you put it into this device and let it fall down to the bottom. So if you can imagine, this is Galton's actual drawing of it, and I got this from Stigler's article on the previous page. If the top here is filled with buckshot, and then you open a gate here and allow it to go down, as the buckshot pass by each one of these pegs in the board, it randomly goes down either the left side or the right side. And in order for one of these buckshot pellets to go all the way to the right hand side, it would have to binomially go to the right at this peg, and then also at this peg, and then also at this peg, and so on all the way down, and it would have to navigate its way through these ones. Now there's some different permutations along the way, so it doesn't have to be exactly that path, but the end result is that you end up with what looks like a normal curve at the bottom. Here's a modern day replica of the Quincunx, and you can see that it's got a stable base on the side. It rotates. It's got a peg within here so that you can rotate the device up and down, covered in a glass casing so that the pellets don't fall out. So this is when the board is essentially armed. It's armed, and then you flip it over as shown on the right hand side, and the balls navigate through here. And you can see that the buckshot pellets conform to what look like a normal curve. This is, according to Stigler, the genesis of Galton's theorizing about where correlation comes from, or his devising of the idea of correlation. And Galton originally referred to it as correlation to indicate how 2 different variables relate with each other. Now here's a set of data that I devised and a formula at the bottom. There are a number of different formulas for correlation, the Pearson product moment correlation coefficient. This is one of the less common formulas. I like this formula, however, because it really shows us what the numbers are doing in a way that other versions of this formula don't do. All the different formulas give the same answer for the Pearson correlation, but in this one you can see what's going on in an easier manner. If you use the Graviter and Wallnow textbook for undergraduate statistics, there's a similar version of the formula for correlation compared to this one. But again, most textbooks don't use this particular formula. At any rate, so we have two variables, x and y, and I've got some numbers here. There are 10 observations, 10 pairs. So imagine, if you will, 10 participants in a study. Each participant is measured on both variable x and variable y, and so these numbers pair up. 2 and 7 are for the first individual, 2 and 5 is for the first individual, 2 and 7 is for the second individual, 4 and 5 for the third, and so on. So in order to calculate the formula, as it's done at the bottom, what we need to do is get the sum of squares, that's this term here, x minus the mean of x squared, and then add them up. That's the sum of squares for variable x. We do the same thing for variable y. And then we get the product of the deviation scores. The sum of the products of the deviation scores goes in the numerator of the formula. So first we'll do the sum of squares for variable x. You simply take the mean of variable x. If you take all these scores, add them up, they'll sum to 50. Divide by 10 and you have the mean of 5. Now subtract that number from each score. And this shows you how far that individual score is from the mean for variable x. So our first participant is 3 units below the mean for variable x. The third participant is 1 unit below the mean on variable x. The last individual in the series of 10 is 3 units above the mean of variable x. The next step is that you square the numbers, following the progression on top for the column headers. X minus the mean of x, that's the deviation score, which is represented in the middle column. But we square those numbers, so the negative gets lost, negative cancels out when you multiply by another negative. So negative 3 times negative 3 gives us positive 9. And you continue that operation throughout and then add them up. And that's going to go in the bottom down here for the sum of squares for variable x. You can see that value right here. And we do the same thing for variable y, using the mean of variable y. If you sum all these scores, they'll add up to 70. Divide by 10, you have the mean of variable y. Subtract the mean of variable y from every score on variable y. 5 minus 7 is negative 2, etc. Then square those numbers, add them up, and you have the sum of squares for variable y. Now those two values form the denominator, and since they've been squared, we're going to unsquare them by taking the root. The numerator, on the other hand, is the cross product of the deviation scores of x and y. So this is the deviation score of x, which is to say it's x, every score of x minus the mean of x. Take the cross product of that with the counterpart over here in variable y. Negative 3 times negative 2 gives you positive 6. Negative 3 times 0 gives you 0, etc. Now, one way to think about this is that the cross products form what we can think of as the signal in a signal-to-noise ratio. So the correlation coefficient is formed by the signal, which is the sum of the cross products, over the noise, which is the amount of variability inside each variable by itself. Now these are not different groups, they're the same people measured on two different variables. So we're looking to see how these variables correlate with each other, and that's the cross products. But we also need to measure the amount of variability inside that variable. So the signal is 26 and the noise is 36.987. If the signal is large, you'll see it represented here by a confluence of positive scores or negative scores. Of course, you can have a negative correlation, in which case you'd see it here. The important point is that the signal has to be large relative to the amount of noise that you have. And you can see that that is the case here with a correlation coefficient of 0.703, which would be considered a very large correlation. 0.1 would be small, 0.3 would be medium, 0.5 would be large, following the benchmarks put out by Jacob Cohen many years ago. So now let's see what happens when we examine the data in a scatter plot. Well, I've got some animations here. So these are the three numbers that we need. The sum of squares for x, the sum of squares for y, and the sum of the cross products. So the computations are not that difficult. Now here's a scatter plot that I produced using SPSS. And one of the things to note here is that when you have a strong correlation, the measurement points, which are placed at the xy coordinates. So if you go back, the xy coordinates, this first one would be 2 and 5. So now we can locate that person 2 on x and 5 on y. That first case is right here. That dot represents that first case in the series of 10. So each of these dots is the xy coordinates of one person on variable x and variable y. And if you have a strong correlation, the dots will be relatively close to the line of best fit. When you go into SPSS and ask for the scatter plot, you have to additionally add the fit line to the scatter plot, which I've done here. It tells us also that r squared is 0.494. That's the square of the correlation. If you have a correlation that's weak, the dots in the scatter diagram will be further out. Another way to think about this is if you map the participant numbers on the x-axis and the residuals on the y-axis. The residuals are determined by the slope and the intercept. It's the predicted value of y. So this would be the predicted value that the line going through here is the predicted value for y. This is the actual value. And the difference here is the residual, or error of estimate. So you'd have to go into the regression equation to get the sufficient numbers for that calculation. I won't do that here. I did this using SPSS. That is to say, I got the residual values from SPSS and then I graphed them in Excel, added the red lines. So the red line shows how much error of measurement there is. The point here is that if you have a strong correlation, these errors will be small. And you can see this one is almost perfect, this one is very small, these ones are fairly small, and these are unstandardized residuals. If you have a weak correlation, you'd expect to see a lot more distance between this line and the dots, showing larger residuals. So let's take a look at a weak correlation and see what happens. Here's another data set. What I did here is I kept variable x as it was in the first one, and I rearranged the numbers on variable y so that the numbers here are less sequential in relation to x. I basically just jumbled them up so that some of the higher scores appeared earlier on. Not so much that it would become a negative correlation. It's still positive, but as you can see in the computation at the bottom, the magnitude of the correlation is pretty weak, at least compared to the previous one. Now, one of the things that I mentioned before is that if the magnitude of the correlation is strong, you'll see a confluence of all positives or all negatives, or mostly positives, mostly negatives. In this case, we see a number of zeros because the various different deviation scores are matching up with zeros. And you also see some negatives. So the negative valences are canceling out the positive valences, making the sum much smaller. So our signal-to-noise ratio, the noise has stayed the same because I maintained the same digits in here in the series of variable y. I just rearranged them so that they're less sequential in terms of having higher scores at the bottom of the scale. So the sum of squares, which is the noise, remains the same in this artificial example. but the signal has become much weaker. And what happens now is that our signal-to-noise ratio is no longer very impressive, and the correlation is much weaker. Let's see what happens when we look at the residuals. Well, first here's the scatter plot. You can see that the scatter dots are much further away from the line of best fit. Now the residual plot shows exactly the same information, it's just that we're looking at the residuals instead of the raw scores. And so with the residuals, the predicted value for y, again that's along the horizontal line here at 0, the 0 represents the amount of residual, and you can see that some of these residuals are quite large. There's still a few that are pretty close, but overall there's a much greater amount of residual for this weak correlation. So that's an exploration of the nature of the signal-to-noise ratio when you're dealing with correlation. Again, we would expect to see that over here in the sum of the cross products with a very large positive or negative value in relation to the amount of noise. Thanks for watching. I hope you found that useful.